Waves. Now we're going to start talking about waves. What's a wave? So I want you to pause the video, see if you can write down, and whatever, maybe it'll take you 5 minutes, maybe 10 minutes to ponder. What is a wave? What is a wave? I'm going to say it, but see if you can just, even prepping your mind, maybe you'll not be able to write something down, but what can you say about waves? What do you know about waves? What is a wave? Pause. And we're back. So here's my definition of a wave. Let's go up over here and we'll talk about some wave phenomena. It's really powerful. We've studied motion. We've studied things like energy, momentum, forces. We've studied rotations and oscillations. So now let's study waves. Super important, and we've kind of built up to this, the ability to do this. Waves, what is a wave? And here's my definition. It's a traveling, well, it's a common definition. It is a traveling oscillation. It's a traveling oscillation or vibration, if you want to call it that. So traveling, I can talk about in terms of translation, that is moving from here to there, translating from one position to another. And oscillation, translation, so I can talk simply, in these cases, we're going to have a constant velocity. Now you can have variation in velocity, but for an introductory course, we can just keep that at constant velocity traveling along. We've got a displacement, delta x in some direction, whichever way that is, a time, delta t, and a velocity, which will keep us constant now. So that's an easy relationship, easiest kinematics you can do. Oscillation, what have you got? Well, three concepts that talk about the rate of rotation. High rate of rotation, short period, high frequency, high angular frequency. Amplitude, low amplitude, high amplitude. So basically two terms here. We've got oscillation, rate, and amplitude. Okay, cool. And here's rate of travel, right? So we can think of a wave as a way to transfer energy or information. We need to look at the anatomy of a wave, and there's two types. Good to know these two types and break it down. We'll look at some wave phenomena, which fall into which type. We'll relate the frequency of oscillation to the velocity of traveling, which will be the velocity of the wave, to the wavelength. And you'll have a good understanding of that. And a lot of people don't, because we learn this stuff as fast as we can, taking lots of courses. But you can have a little more subtle understanding than most do. We'll talk about the causality. What causes the frequency? What causes the velocity? What causes the wavelength? What determines them? Okay, so we'll be careful to think physically about a very simple mathematical relationship. We'll look at more phenomena like diffraction, interference, and things of that nature, Doppler shift, beats. And we'll look at a more sophisticated way of handling waves in the mathematical description, which is going to be a cosine or sine, sinusoidal term, which varies in space and in time. Okay, so it's going to have two terms in that sine or cosine function. Okay, and then you can write the equation of motion for a wave, which we're going to see as a second order differential equation. Okay, so let's get to the anatomy of a wave. Nice and easy stuff. The anatomy of a wave, two types. There's transverse and longitudinal waves. Okay, and I'll show you those in just a second, but let's do it on the board first. So a transverse wave means that the oscillation is perpendicular to the translation. That is, it wiggles this way while it goes that way, for example. That's all that means. With an oscillation, we've got the rate of oscillation and the amplitude of oscillation, the blue one. The traveling speed, or the wave speed, is going to be just going along that way. Oscillation perpendicular to the translation. Longitudinal, the oscillation is parallel to the translation. Okay. Again, oscillation, rate of oscillation, and amplitude. Back and forth this way now if I'm traveling that way. Oscillation, and then I travel with the wave speed. So let's put those together and see what we've got. So if we do this, we can start anywhere we like. Let's start here. I'm going to go along here. And first I want to look at that oscillation. Where's the amplitude? Would it be here to here or here to here? This is usually called peak to peak. Okay? This right here is what we refer to as the amplitude. So how tall one peak would be, right? Crest is another word. And then this would be the amplitude, and the peak to peak would be 2a. We use that a lot in electrical circuits and things like that. So just know the difference. It's not a big deal. Come down, complete a wave, and keep on going. So now the interesting thing is we think of this wave as a thing traveling at this speed, wave velocity here. So we think of it as moving along, and that disturbance does. We'll get into that in a second. All right, so what I get out of combination of oscillation with translation, and you can see that I translate, I oscillate. Okay. What I get is the wave. And so what emerges, an emergent property, something that emerges, is from here, well, let's do it from the peaks. From one peak, that's not a wave. Where's the wave? Oh, I've got to go all the way to another peak, right? And so that would be the length of one wave or one cycle. Of course, we call that a wave length. What symbol should we give it? How about L for length, right? But it's not exactly length, it's the wavelength, it's the lambda, and X with the missing upper right there. Lambda of the wave. And that is in, say, meters, or whatever length unit you want, per cycle. It's really helpful to keep that cycle term in there. It'll help keep some things straight. So that's meters per cycle is the wavelength. So if you put these two together, what emerges is the purple. And if you put red and blue together, you get purple color. So there you go. All right, where else is the wave? If I start here, the wave here, and I go here, is that a full wave? No, it's just one bump, right? I have to, this is at the same place, but it's going down. I need to be at the same place, but going up again if I started up. So one wavelength would be here. Here to here, one hump would be half a wave, right? If that's true, how much is this? How much is half a hump? Well, that's 1/4 of a wave. And it's important to be aware of that. It's not a big deal. But just make sure that you right away see that this is half a wavelength, that's half a wavelength, that's a quarter, that's a quarter, that's a quarter, that's a quarter, that's a full from here to here, or trough to trough, or any other two. Fine. So nice and easy to see on a transverse wave. But when we get to longitudinal waves, well, we've got an oscillation that's along the line of our travel. And so good luck drawing that. Let's try it. Oscillation. It's a mess. It's a mess. Where's the amplitude? Well, on this picture I can say, okay, here's amplitude here, and here's an amplitude there, my oscillation. I can oscillate fast or slow. And I can travel fast or slow. I don't know, from the back to the back. Let's see, from the crest to the crest, from the back to the back, from the there to there. Is that a wavelength? Maybe that's a wavelength, right? Wavelength there. But really hard to see. Consequently, even though a good deal of phenomena is actually, this is what's happening, we will sometimes draw these waves often as a transverse wave. So don't be fooled. If you know the phenomena is a longitudinal wave, but it's drawn this way, that's just because it's a lot easier to see, right? Okay, so let's take a look at this. The slinky's great. So which kind of wave is this? The oscillation is parallel to the translation. You can put it on the ground, do this. So that one was a longitudinal. This is a transverse wave where I oscillate up and down and it travels over there. And I can just see it as a pulse that travels along. Let's take another look. Here's a string. I can do a pulse here. And you can see it travels from me down to there and back. And so it's a wave pulse, just a little blip, right? A little disturbance that travels, a little energy, if you want to think of the energy of that movement, traveling back and forth. So it's traveling and it's going like oscillating this way as it travels that way. That would be a transverse wave. We can use a wave machine This is kind of fun. And we can say, all right, how are we doing on that one? Oscillate. Which way is it going to travel? That way. I'm going to oscillate perpendicular to the translation. Let me come back to this. If I oscillate parallel to the translation, longitudinal, transverse. So do it with a slinky or whatever. So what phenomena, like what is sound? You know, what is, there's a string wave. I've got sound, like, this is great. Sound, and we've got guitars, right? So, ooh, time to tune that guy. So we'll explore this guy a lot more. Kind of neat. We've got sound. All right, so we've got a lot of phenomena here. Oh, let's see. What falls into the transverse category? What actually moves transversely? Important point over here is that you cannot have transverse waves inside of fluids. You can think of the ocean as going like this. It's actually kind of sloshing back and forth while it goes up and down. So it's got a bit of a circular to it on the surface. But within the fluid, and by a fluid I mean a gas or a liquid, and we're getting to that next, you can't have this. If you think of it, if you have a string and I pull this piece up, it's going to pull this piece up, which pulls this piece up, which pulls this piece up. And that's because of that connection. With fluids, they're not connected. So I pull this piece up, it isn't holding on to this piece and pulling it this way. However, if I compress it, I get what we call a compression or expansion, rarefaction. So expansion, compression, pressure wave, things like that. So in a fluid, I can have that, but I can't have that. All right, important little note. String waves, you just saw a string oscillates perpendicular to the translation. The S earthquake wave, S for secondary, means it's slower. You can almost think of it as shear. It's a secondary wave, so it'll get there second. When an earthquake happens, you get two waves. This one gets there second. It's the up and down rolling of the ground, if you're lucky enough to see that, and safe at the same time. Light, you might ask, which one is light? Well, light is a transverse wave. There's visible light, there's light that our eyes can't see, just like there's radio stations that you aren't tuned to. We're not tuned to those. Light is has an electric field and a magnetic field. These fields are perpendicular to the traveling speed, the velocity of light. What does it go through? We'll talk about that in a second. For slinky, well, slinky, you saw you can have both, so I could have put slinky up here too. You can have transverse and longitudinal, that's kind of nice. P earthquake waves is the back and forth like this that travels along. It travels faster. Okay, so that's the primary wave. This can go through fluids. That cannot. Okay. Sound is an oscillation. Now, it doesn't just have to go through air. It can go through steel. In fact, we'll talk about this later, but it goes through steel about 11 times faster than air. All right. So we've got these different types of phenomena. Let's talk about light and sound quite a bit. In fact, in general, let's go over here and talk about this concept of media or a medium. Medium, not small, large medium, but some material or something that the wave travels through. So the medium could be your string, or your slinky, or the water, or the air, or steel, right? And the medium, this is really important, the medium oscillates, but does not translate. It does not translate. The disturbance or energy or information travels, but the medium just oscillates. Okay, we're going to come back to see that in a second. Let's go ahead and do that. The medium oscillates. So if I can come back here, I can see that any one of these points is not traveling. So the wave is not like a physical thing that's traveling, it's a disturbance. As I pull this one up, the other ones next to it get pulled up. If it's traveling to that side, when that goes up, it pulls that up, pulls that, pulls that up. Right? And then it goes the other way, pulls that up, pulls that up, pulls that up. But the medium, which are these little steel rods, they just oscillate. the disturbance travels. Important and kind of deep, and we'll get to that later. So that means in sound, when I talk, the air here vibrates. Well, it vibrates from down here. The air vibrates this air, this air, this air, this air, this air, and the air that's already at your ear vibrates at whatever rate and at whatever amplitude. So, that's interesting. Two questions come up. What is light? Sound, some vibration in material, through material, like longitudinal oscillation. What is light? Well, light, we said, is a transverse wave of electric and magnetic fields. Really cool stuff, weird. What does it travel through? What's the medium of light? And the medium of light, some people say it's nothing. Sunlight comes through virtually empty space. Light will go through a vacuum. You can look at inside, you can create a vacuum and look and see the stuff inside. It might be better to say the medium for light is space-time. Okay, just for later, space-time. All right, let's do a couple more things. Amplitude and frequency, what do they mean? Let's look at sound and light. Those are really interesting examples. So what does it mean to have amplitude? Here, let me block it. Maybe you saw it. What does it mean? Think about it. What does the amplitude of sound mean? If you make it higher, more or less amplitude. What does the amplitude of light mean if you don't cheat there and make it more or less? What about frequency of sound? What does that change? And what about the frequency for light? Light and sound are very, very different phenomena. Speeds are very different, right? Sound travels about 340 meters per second. Okay? That's about 700 miles an hour. Light travels about 300 million meters per second, about 1 million times more, right? So, okay, so for sound, the amplitude might just be the loudness, right? The loudness, the amplitude of the oscillation to your ear is loud. Our biological response, our ears, are modeled as a logarithmic function. So if it gets, the amplitude is 10 times more, it isn't 10 times louder, which is kind of a good thing because the amplitude range is insane. You might look that up. For light, if it gets more amplitude, it's brighter. If it gets less amplitude, it's dimmer. Softer, louder, brighter, or dimmer, brighter. Parallel. Frequency, what's that? For frequency, the rate of oscillation. For sound, it's the pitch. You get a high frequency, it's a high pitch. If you make a high note, you'll feel your throat oscillates at high frequency. Or low. You can feel it vibrate at different frequencies, okay? So that's translated into sound to high frequency, high pitch, low frequency, low pitch. What about light? That gets interesting. With light, visible light gives you the color. So different frequencies give different colors. It's kind of neat that light and color all have 5 letters. Red, orange, yellow you can't draw with a pen anyway, so might as well leave that out. Green, blue, violet. Red, orange, yellow, green, blue, violet. You should know the color of the light rainbow colors in order. Red, orange, yellow, Roy. G's the middle name. Biv, blue, and violet. Okay? And color also, you can do that too. But there's also light that we can't see. It's non-visible light. Okay? So what's the difference? I'm going to do this really quickly. Take a look at light in particular, and then we'll look at the energy of waves. So you've got all this. One thing to realize is, let's see, I've got the frequency of red. Let's just jump to the frequency of, let's say, blue or violet. Let's just do violet. The frequency of violet. Then I've got the frequency that I can't see, so I'll go like this. So you can see it. Ultraviolet, more than violet, hint, hint. The frequency less than violet, you can't see that unless you're a bug or an alien. So that's infrared before or inferior to red, so that gives you a hint. And then we've got micro, And we've got radio, a whole range of radio frequencies, microwave frequencies, infrared, red, ultraviolet. Then you can't see these. Ultraviolet, you got the frequency of X-rays, and you got the frequency of gamma rays. Which has higher frequency? You can't look at the colors and tell. It doesn't make your head oscillate. But it turns out that the greater than symbol goes this way. Turns out the violet actually oscillates with a higher frequency. And so ultraviolet, more than violet, is a higher frequency. Higher frequency. Less than red, or inferior to red, is infrared. Less than that's microwave, and less than that's radio wave. And that is tied to energy. So we're going to talk about that. Before I do that, let me make sure that we've got these colors in order, right? From red, orange, yellow, you know this. There's my yellow. You can't draw yellow. I can't draw yellow. Green, higher frequency, blue. I don't think of blue as high frequency, really. I kind of think of cool blue. And violet. Red, orange, yellow, green, blue, violet. Roy G. Biv, make sure you know those rainbow colors. Inferior to red or infrared, more than ultraviolet. Good. So now the next question that I have is energy. What determines energy? I mean, energy of a wave. Let me see, you know this. Let's talk about the energy of oscillation. That's the kinetic plus the potential energy of the oscillation. And we studied that that is always the same number, so I can look at the maximum kinetic energy. We studied that's 1/2 mv max squared, which happens in the equilibrium when it's coasting on through, right? That's equal to 1/2 m, I'll write it this way, omega a squared. Of course, I can write that as 2 pi f squared. That means that my energy is proportional to the frequency squared and the amplitude squared, which makes total sense for a wave. That the energy of a wave, and this is very, very useful information, important to keep that in mind. That takes more energy than that does. Higher frequency, more energy. That takes more energy than that does. More amplitude. Louder sound has more energy, right? A higher pitch actually has more energy, right? A brighter light has more energy, amplitude. And then the colors and even the non-visible range or spectrum of light, higher frequency, higher energy. Know that and you're good to go. Next thing we're going to do is look at the relationship between oscillation frequency, wave speed, and the emergent property of wavelength. And a nice easy algebra equation, but you have to keep the physics straight to get it right.